Okay, so now let's talk about deformation of contour. So this is a technique for making evaluation much easier. Okay. Suppose F has n poles, so Z1 to Zn. Okay. The question is, find a contour around, let me write it as C. Find the value around C. Okay. So here's a trick. First, find in terms of simpler contours. So that's the trick. This let me try it again. This C could be very complicated, complicated, contour. But there's a way to write it in terms of simpler contours. So integral of f over simpler contours. Okay. So first draw small circles. So CK is C to the Z minus ZK equal to RK, right? So small enough circles so that they are contained in the interior of C. So let me draw it again. This is C, and this is CK, and draw a circle around it. Call it CK. Okay, this is just a circle. All right, so we do this for all of them. So, if they're very close to the boundary, it has to be smaller. If it's inside, you can make it small, but if you're very close to the boundary, you have to make it smaller. Okay, C1, C2. All right, second step. Form a large contour whose interior, large contour C tilde, whose interior does not contain the poles. Okay, so let me keep it simple and do it for just two of them. So this is C, and what we do is, so this is C1, and we move like this. So we go up, we cover it, and then we come down like this. And come here, connect, make the circle, and then come back. Okay, so C tilde is C union all the other guys. C1, but clockwise, so reverse orientation. Maybe like this. Okay. All right. Okay, so this is the domain of interior of C. Since interior of C tilde does not contain the poles, the Cauchy Gauchat gives C tilde of F is 0. Right? Okay, so now let's use what C tilde is. So we have F of C, and now it's clockwise, C1, C2, so on, equal to 0. But remember, right, by convention, this is the positive and clockwise is negative. So we have contour over C is equal to the summation of the clockwise as well, counterclockwise. We moved it and used minus sign. Okay. So yeah, we wrote complicated contour in terms of, circles. So that's the beauty of this technique. Let's see it in action. So we'll do one long example with many parts. Find the contour. So z squared plus 3 for the following. C equal to unit circle. C equal to the circle around 2i. And finally, the circle of radius 4. Okay, let's start. Number 1 step, find the poles. So we have C is equal to so we have z minus I square root 3 times z plus I square root 3. So let me draw it. Square root 3 is about 173. So 1 is over here, minus 1 is here. Okay, so these are the two poles that you have to keep track. All right. Let's do part A. This is immediate because F has no poles in the interior in C strictly less than 1, right? So this is the unit circle, and this is the interior, and the poles are outside. So, okay, that means the contour over this is 0. So that's easy. Now this circle, 2I is over here. So C equal to, now this guy hits 1 and 3I. Okay, so it only contains I square root 3, which is over here. Okay, so let's see. Okay, so first let's do partial fractions. And the reason is, in order to isolate the integral that has the pole. So c squared plus 3. And we found the roots, so I might as well write them. Okay. Right, so you have 2I square root 3. And then okay, so that's the partial fraction. So we have the integral. We split it by linearity. Okay, good. By Cauchy-Groschadt, this is 0. Because it has no pole inside the circle. Its pole is down here. But yeah, this guy has a pole. Okay, good. So let's write the circle. This guy. Okay, but you know, this contour is not convenient, right? So we have this circle, and then we have I of square root 3. It would have been more convenient to have a circle around the pole. Then it will make the computation easier here. Okay. So by deformation of contour, we change to the circle z to the minus I square root 3 equal to 1. Okay. So, okay, why is this convenient? Let's do our parameterization. So 0 to 2 pi. Right, so the bottom guy just becomes e to the I theta, right? Because this is a circle. This is a circle around square root 3. Right, and then the top guy is e to the I theta plus I square root 3. Good. Okay. So these guys cancel out. These guys. And the I is also canceling out. Okay, so anyhow, this guy, we talked about it in the last clip, it's 0. So you have this, and so you just get 2 pi I square root 3. So you just get pi I. And that's it. So let me write down what we did. So z minus 2i of z squared plus 3, it will be pi I. And right. And yeah, so so we did deformation of contour. We did deformation of contour in order to write a clean parameterization. So it's a trick, it's a tool. Okay, so let me now finish with the last part. So C, take z to be, take the contour to be z to the 4. Now this guy is massive, and it contains both roots. Right, so it contains both roots. So going back to the partial fraction, what do we have? In the previous case, we said this is 0, but it's not now because the pole is right here inside the contour. So this is okay. Now we already computed this piece that was pi I. So now we have to find this guy times this 2i squared root 2. Right. So I won't go into too much detail, but again, you want to have a nice clean parameterization, so you deform it around the pole. So minus minus I square root 3. So let me write it as plus to keep it clean. Okay, so now again, you can do your what we did above with coordinates. And yeah, so you will get 2 pi I. You will also get pi I. So the total integral is pi I Oh, right, there's a minus. So yeah, it will be minus minus pi I. So I got 2 pi I. Okay, so that's it. Thank you.